Welcome to our fluid mechanics dissection project. Our chosen device is the Hoover wind tunnel vacuum. The ambient air and dust particles are drawn by the agitator and the airflow generated by the motor impeller assembly. This air then travels through the intake housing towards the assembly, which connects to the dust bag chamber. As a throw flue system, the air passing through the motor must be effectively filtered. Therefore, there is a fine filter at the end of the dust bag housing that prevents smaller particles from clogging the motor impeller assembly. After that, the air is filtered again to remove all particulates before being released into the outside. The total energy of the air does not change as it travels through the inlet and the hose. The air speeds up in the hose as the pressure is converted into kinetic energy along the streamline. We cannot use Bernoulli's equations without assumption since it applies to only steady and viscid and incompressible flow. The air is certainly not incompressible. However, it's accepted that if air's velocity is less than 100 meters per second and air's density changes less than 5%, the air is assumed to be incompressible. We also ignored the effect of gravity. With these assumptions, we can apply Bernoulli's equation through the path that is tangent to the velocity vector of the flow from the intake through the hose to the dust box. A low Reynolds number describes the laminar flow pattern for dust particles, while their shape, size, and viscosity can increase the Reynolds number and make the flow turbulent. A higher viscosity fluid like honey would make the Reynolds number smaller, and if the pipe diameter is bigger, the Reynolds number will also be higher. The critical Reynolds number will decrease with increasing surface roughness as the relative flow rate with the vortex decrease, which reduces drag. The Reynolds number calculated for our machine is 1602. Centrifugal pumps function by increasing the total pressure of the fluid. The core component of the centrifugal pump is the rotating impeller installed on the motor shaft with the air entering from the dust bag into the eye. Then the impeller blades locally increase the kinetic energy of the air spinning azimuthally. While being redirected by the volute, most of the kinetic energy is converted into pressure before exiting through the diffuser into the motor chamber for cooling. At this point, the flow again falls under the Bernoulli assumptions as earlier. As air enters into the motor chamber, which is wider than the diffusion section, we can determine that the pressure increases while the speed decreases. Finally, this air, which has lower pressure than the atmosphere, is ejected as it passes the final filter. Quantify the characteristics and performance of the pump, we will determine the specific diameter and efficiency. The vacuum has an input power of 1200 watts and was tested to have a capacity of 77.5 CFM. The impeller is about 0.115 meters in diameter, and using 20 kPa as the average household vacuum suction, we calculated the values to be 6.8 and 61% respectively. The specific diameter aligns with the fact that this is a centrifugal pump. Selecting a high specific diameter pump makes sense, as one would prefer a high delta P generated to suck up heavier dust. The low efficiency is attributed to the air duct's geometry and viscous losses, which we will discuss later. The tubes, tools, and attachments in the vacuum make the flow much more complex. Firstly, the tubes leading to the impeller are much narrower than the impeller housing. This sudden increase in diameter along the steady flow creates a Venturi effect, which occurs when steady flow of a fluid is forced through a narrower section of pipe, causing a rapid increase in velocity and drop in pressure, increasing the flow into the impeller. As the tube's curvature increases, the centripetal force that causes the fluid to move in a curvature that can cause a pressure gradient that creates regions of flow of high pressure. According to Bernoulli's equation, pressure tends to decrease as velocity increases. However, tubes and attachment on a vacuum are also a limiting factor for its performance. Vacuum tubes like the ones from our dissection are wrinkled. This irregularity on the boundary conditions causes the flow that would likely cause a separation due to viscous effects. Length and diameter of the tubes also contribute to viscous losses. The longer the tube, the longer the pressure will drop due to viscous interactions along the longer wall. Conversely, an increase in tube diameter will likely cause an increase in pressure due to the same viscous interaction with the boundary. All of these factors contribute to the tube's conductance. Conductance is a measure of volumetric flow divided by pressure drop along the tube or pipe. What this does is allow us to quantify the total effects of viscosity along a tube and geometry into a single value. This value tells you the amount of fluid that will effectively be able to go through your components, which helps drive pump selection. A pump can spin as fast as it wants, but if the conductance is too low, it will be heavily limited by the amount of flow that is able to reach it.